This lecture provides a detailed, step-by-step guide on how to simulate a 3-degree of freedom RPR robot manipulator using Simscape Multibody and Matlab Simulink. The RPR robot, as shown in the figure, consists of 2 Revolute joints and 1 Prismatic joint. We will perform the following tasks. Attach coordinate frames to each link of the robot using the Denavit-Hartenberg convention. Construct the Denavit-Hartenberg parameter table. Derive the forward kinematic transformation matrices. Use Matlab Simscape to simulate the robot manipulator according to the coordinate frame assignments defined by the Denavit-Hartenberg method. Compare the simulation results with the analytical results obtained from forward kinematics calculations. According to the Denavit-Hartenberg method, coordinate frames are assigned to each link of the robot as illustrated in the figure. Based on this assignment, the D/H parameter table can be constructed as shown on this slide. For more details on the procedure, you can refer to the previous video lessons, or consult the theoretical explanations provided in the textbook by John Craig, as referenced here. From the Denavit-Hartenberg parameter table, we can derive the forward kinematic transformation matrices as shown on the slide. We attach an extra coordinate frame, E, to the end effector of the robot. The global coordinate frame is defined using the world frame block in Matlab Multibody. The positive directions of the X, Y, and Z axes in the default world frame are shown in the figure. Now let's start the simulation. In the command window of Matlab, type the command SMNU. A new window will appear with a multibody template. Delete the unnecessary blocks and keep only the 3 basic blocks that define the world frame coordinate system. On the menu bar, go to Simulation and select Save to save the file. The file name and save location can be chosen according to your preference. Double-click on the world frame block and the mechanism configuration block to check their parameters. Next, take out a cylindrical solid block to create the base plate of the robot. Double-click the block to open its settings, where you can set the dimensions and choose the color. Then, go to the Frames tab and select New Frame to create connection ports. In the New Frame window, set port F1 at the bottom surface of the cylinder and port F2 at the top surface. Note that these connection ports are aligned along the Z-axis of the block's local coordinate frame. The Z-axis is shown in light blue and labeled with the letter Z at its tip. Next, create another vertical cylindrical block, which is also part of the robot space. Hold the Control key, then click and drag the existing cylindrical solid block to copy it. Double-click the new block to open its settings. Set the z-axis dimension so that the total height of the two base cylinders equals L1 equals 0.3 meters. Keep the same color as before. Keep port F1 unchanged, but delete port F2, as it is no longer needed. Finally, connect the blocks with signal lines and run the simulation to observe the result. We use the tree view in the left panel to examine the coordinate frames attached to each component of the robot. Zoom in to take a closer look at the coordinate frames. We can see that the base coordinate frame in the current simulation is identical to the world frame, and it does not yet match the coordinate frame assigned according to the Denavit-Hartenberg method. According to the coordinate frame assignment based on the Denavit-Hartenberg method, the base frame is rotated by 90 degrees around the z-axis relative to the world frame. Therefore, we need to include this transformation in the simulation. We will use a rigid transform block to convert from the world frame W to the base frame 0. This transformation rotates the world frame by plus 90 degrees about the z-axis. To perform the simulation, take out a rigid transform block and place it between the world frame and the base 1 block. Connect the B port of the rigid transform block to the world frame, and the F port to the base 1 block. Then, open the rigid transform block settings. Under rotation, select standard axis, and set the angle to 90 degrees. After completing the setup, run the simulation to observe the result. Select frame 1 of the base 1 block from the menu on the left panel. Then, zoom in to take a closer look at the frame 0 attached to the robot space block. Zoom in on the coordinate frames. We can see that the frame 0 attached to the base is now correctly oriented according to the coordinate frame assignment designed using the Denavit-Hartenberg method. After completing the base section, we now move on to frame 1. According to the coordinate frame assignment based on the Denavit-Hartenberg method, frame 1 is translated along the positive z-axis by a distance of L1 equals 0.3 meters. Therefore, we use a rigid transform block to perform a translation along the positive z-axis by 0.3 meters, transforming frame 0 into frame 1. To implement the simulation as analyzed above, copy the existing rigid transform block and modify its parameters. The transformation from frame 0 to frame 1 is a translation, so set rotation to none. In the translation section, choose Method, Standard Axis and select the plus z-axis. Finally, set the offset value to 0.3 meters. Joint 1 is a Revolute joint. Therefore, take out a Revolute joint block from the Multibody library and rename it as Joint 1. At this point, select all the components of the base block, then right-click and choose Create Subsystem from selection to group them into a subsystem. Inside the base subsystem, rename the connection ports. The base block has one port connected to the world frame and another connected to joint 1. Since the base structure extends vertically upward, we can rotate the block to make the layout easier to visualize and manage. Next, we create Link 1. In the Simulink library browser, go to Simscape Multibody and take out a brick solid block. Set the dimensions and color as desired. Then, connect Link 1 to Joint 1, and click Run to start the simulation and observe the result. Review the coordinate frames attached to each part of the robot up to this point, and compare them with the coordinate frame assignments defined using the Denavit-Hartenberg method at the beginning of this lecture. Now, let's move on to frame 2. According to the coordinate frame assignment based on the Denavit-Hartenberg method, frame 2 is rotated by plus 90 degrees about the x-axis. After this transformation, the z2 axis becomes horizontal. Therefore, we use a rigid transform block to perform a plus 90 degree rotation around the x-axis, converting frame 1 into frame 2. Set. The parameters of the rigid transform block is shown in the slide. To implement the transformation as analyzed above, take out a rigid transform block. Set up the block parameters as shown in the video. Under Rotation, choose Method, Standard Axis. Then select Axis, plus X to perform the rotation around the positive x-axis, and set the angle to 90 degrees. Next, we simulate joint 2, which is a prismatic joint. Open the Simulink library browser and drag out a prismatic joint block. Rename it as joint 2. Set up the block parameters as follows. In the actuation section, set force to automatically computed and motion to provided by input. In the sensing section, select position to enable the output port for measuring the actual motion of the joint. Next, we create link 2. Link 2 is a long bar driven by joint 2, moving translationally along the z-axis. Therefore, it is represented by a brick solid block. Copy the link 1 block and adjust its dimensions and color settings. Set the length of link 2 along the z-axis to 0.4 meters. The connection port is located at the center of the block, so in the initial position, the link will be centered within joint 2, with 0.2 meters extending on each side. We run the simulation to observe the results. Click on the blocks to check the connections and coordinate systems. We zoom in on the image to inspect and compare the coordinate systems attached to link 1 and link 2. The simulation shows that frame 2 on link 2 is rotated 90 degrees around the x-axis compared to frame 1. This matches the Denavit-Hartenberg coordinate setup. Now, select all components of link 1, right-click, and choose Create Subsystem from selection. Inside the link 1 subsystem, rename the connection ports. One connects to joint 1 and the other to joint 2. Since link 1 is horizontal, rotate the block to make it easier to view and manage. At this point, the file size of the lecture has become quite large, so I need to split it into 2 videos. Please continue watching part 2 of the lecture video to proceed and complete the simulation.